So, good morning, everybody. My name is Julie Dutems, and I'm going to present to you my PhD project called the Thin Passive Film Characterization by Surface Plasmon Resonance. The new results that I will present today are in collaboration with the Laboratoire Hubert Curien and HEF IREIS. Okay, it's okay. During this presentation, I'm going to introduce by explaining what are passive film and what's surface plasmon resonance. I'm going to present the preliminary results that has been leading during the project with the presentation of the experimental setup, a polarization curve and with the SPR, and successive electrochemical impedance spectroscopy and the SPR. I'm then going to continue by explaining the calibration of our system, and then finishing with the conclusion. So first, what's a passive film? A passive film is described as a complex oxide layer that appears naturally at the surface of a passive metal in order to protect the metal against corrosion. If you put this metal into a solution, for example, an electrolyte, the outer layer of the oxide will start to hydrate, but the inner layer will stay a dense oxide layer. The passive film is mostly about 3 to 10 nanometers, depending on the metal, depending on the electrolyte it is exposed, and has a certain permittivity and a certain thickness. It's mainly characterized by electrochemical characterization and mostly by electrochemical impedance spectroscopy. It permits to give the passive material behavior and to obtain the effective capacity of the electrochemical interface, permitting to give its resistivity against corrosion. And with the permittivity, it permits to obtain the thickness of this passive film. All that are crucial information about the film's quality and material robustness against corrosion. The idea here is to use an optical characterization called the surface plasmon resonance, that's very sensitive to permittivity and thickness variation at the metal and the electric interface. It is to use this technique as a complementary characterization technique to characterize this passive film. So, what's surface plasmon resonance? It's described as a collective oscillation of the electrons at the metal and the electric interface. It can be seen as an evanescent wave that propagates at the metal and the electric interface and is very sensitive to any interface variations, such as the permittivity modification into the electric permittivity or the film thickness. There are some requirements on the metal permittivity. For example, the real part of the metal permittivity should be negative, and its absolute permittivity should be greater than that of the dielectric. And the plasmon wave vector is composed of the incident wave vector light and an effective index. And every variation into the dielectric permittivity will induce a variation into the effective index as seen as the surface plasmon. In order to excite a surface plasmon, phase matching must be guaranteed between the oscillation of electrons in the metal and the dielectric. And to achieve that, we can use a prism or a micro-nanostructured surface. It is the latter one that is used in the framework of this project. So the idea here is to use surface plasmon to characterize an oxidation. So while there's an oxidation, it means that there's a consumption of the metal. And an excitation of the surface plasmon with the prisms involves that the metal film is supposed to be extremely thin, about 20 nanometers. Since there's a consumption, there's risks that the totality of the metal is consumed. So, but with a micro-nanostructured surface, it is possible to use bulk metal. So even though there's a consumption of the metal, there's no risks that there's a modification into the seen thickness by the surface plasmon resonance. What happens when there's an incident light on our diffraction grating? So there will be some energy at a special wavelength, at a resonance wavelength. Okay, so there's energy at one specific wavelength that's, for example here, that will be used to propagate the surface plasmon at the interface, and the rest of the incident light will be reflected, and it's this resonance that is measured for our sensors. SPR is a good sensitive technique for census devices. It is well implemented into literatures since many years, and you can find them for example, gas detection or mostly for biosensors. So here's a presentation of the experimental setup used. We do use gratings, diffraction gratings, dipped made of aluminium with a passive film of alumina, with aluminium passive film. It is dipped in water in an electrolyte. Here is the setup. We do have an incident white light. The electrochemical setup is a basic 3 electrode setups, and the working electrode, is a diffraction grating, which here's a picture of what's a diffraction grating. We do have a potential start in order to achieve the electrochemical measurements, and the spectrophotometers in order to measure the surface plasmon resonance. So here are the preliminary results, a polarization curve and surface plasmon resonance. So we have put, as seen here, a diffraction grating into a 3 electrode setups, and we have changed the potential puts into these 3 electrode setups. Here are the electrochemical measurements. At the first part, here we are in the cathodic domain, which means that there's a reduction of the species. And here the anodic domain, which means that we were able to oxidize our system. And during those measurements, we have done the optical measurements. So here is the surface plasmon resonance. And we have extracted the resonance wavelengths, and we have measured all the spectrums during the process. And here is the shift into the resonance wavelengths. And we were able, in real time, to measure this variation into the resonance wavelengths. But at this time, we don't really know about the characteristic of the oxide that we have made growth. So in order to achieve that, we have made some successive electrochemical impedance spectroscopy while measuring with the surface plasmon resonance. So here are the electrochemical data. So for each dot here, one EIS has been leaded, which permits to give the film capacity of the electrochemical interface, and we were able to extract the oxide thickness. And then we were able to do the same with the SPR data. We have extracted the resonance wavelengths obtained experimentally, and we have correlated them with the theoretical resonance wavelengths. But as you can see, there's a small shift, even though between the electrochemical and the optical data. But the curve seems has quite of the same tendency. And if we have done a shift into the initial film thickness, and we can see that there's a good superposition between those data. So actually, there's an uncertainty with the initial oxide thickness with the optical data. So in order to try to overcome this problem, we have imagined a calibration system with a sensor with a known alumina thickness that has been deposited on the sensors. So some non-oxide thickness layer has been deposited on diffraction gratings. So here is the concept of the sensor with the center of, well, one sensor means one alumina deposition, On the center, we do have a diffraction grating with pure aluminum deposition. And on each side, we have aluminum and alumina deposition that has been done. The sensor design and diffraction gratings has been fabricated by photolithography and replicated with a nano imprint in order to obtain many different sensors with exactly the same parameters. And the metal and oxide deposition has been done by HEF Ireis, by magnetron sputtering. 4 alumina thicknesses has been deposited, 5, 10, 15, and 20 nanometers. And we do have 8 samples in total, 2 for each alumina thickness. Here is a picture of one of these sensors. So the idea is to have many different points of measurements in order to try to have a good quality of measurements. Well, so here for the measurements, we do have a white light. We are in the air. We have a white light that is incident with a certain angle on our diffraction grating. And with the spectrophotometers, we observe the spectrums. So the grating have a certain period of 630 nanometers. And as you can see, there are 2 resonance wavelengths on our spectrums. The first one is induced by 1 diffraction order and is situated at a resonance wavelength at 435 nanometers. And there's another one that implies that there's another diffraction order that excites another surface plasmon at this interface and permits to obtain another resonance wavelength. And the measurement has been leaded on the different aluminum thicknesses. And we were able to observe this shifting into the resonance wavelength and to obtain a different resonance wavelengths for every thicknesses. Then a comparison of the resonance wavelength shifting between the simulation and the measurements has been leaded. So in orange, it's the resonance wavelength shifting for the first plasmonic zip, the first one, not the second one, for the first one for the simulation. And the blue one corresponds to the measurements. So as we can observe, there's a well correlation between the measurements and the simulation. In order to start validating the model, we have done some SEM measurements. Here is the SEM measurements on the 20 nanometers alumina deposition sample. So here in this part, it's the aluminium. And this part corresponds to the oxide layer that has been deposited. And the thickness of the alumina layer here, it depends of the part of the grating. So we can have 17.49 nanometers or 20.14 nanometers. So yes, we are around 20 nanometers, which can explain the difference between the simulation and the measurements. So in conclusion, during this project, we were able to use SPR in order to detect aluminum passive film during an electrochemical process, and it has been validated with the creation of an experimental setup. We have designed the sensors and done some data processing tools. And we have started a calibration of the system in order to start to validate the model. And well, some measurements are still ongoing, but it's quite promising for the moment. Thank you for your attention.